Okay, so good morning. So we were looking at block cipher, and in the last class we looked at uh, DES, Data Encryption Standard, which was discovered in 70s by IBM, and it was widely used till late uh, 2000 or something. So basically, as I mentioned, so once in 1997, in fact, before that, people started thinking that now the time has come to replace DES, and then just to increase the security, they proposed, as I mentioned, double DES or triple DES kind of thing, and then, as I mentioned, in 1997, it was broken. DES was broken finally, and then there was a fresh call for proposal from NIST was issued that now we should have a new version. Now you see that. So today I'm going to describe this AES, Advanced Encryption Standard. It's another block cipher, but this is not based on Fistel network, But this also involves some of those S boxes techniques and a couple of other things. And again, this is also very lengthy. You will see, you know people think that if you make a lot more encryption, probably it is secure, right? But good thing is that still it is unbroken. So maybe this is a good opportunity for you. So if any of you can actually crack this crypto system, right, you will get a paper, obviously. Second, you will get fame, and third, you will get double A grade, right? So, so just try, and if you can crack AES. Anyway, this AES has been, even now people are thinking the key size from AES, which is around 128 bits, 192 bits, and 256 bits. Okay, that's the key size. Now people are developing another area very recently, what is known as DNA cryptography. So basically, on the structure of DNA, basically you are encoding the stuff and doing certain things, and there the key size is more. So basically, people are doing different kind of things uh, in that direction. Anyway, so let me describe this. First, little bit history about it. So as I mentioned, Advanced Encryption Standard on January 2, 1997, NIST asked for replacement of DES, and September 12th, 1997, formal call for proposal were issued. Okay, and there were many submissions actually, So, and there are certain security requirements that were posed, So basically, key idea was it should be secure, the cost effective should be there. Its algorithm and implementation should be easy, all these things should be easy basically. So actually, Renzel proposed and his team proposed three versions of AES: AES 128, AES 192, AES 256. So this is a key size. Okay. So we have 128 bits, 192 bits, and 256 bits. I am going to describe you AES 128. I will give you the general thing. It's almost similar to that. So length is 128 bits, supports key length, so basically 128, 192, and 256 bits. Should be available worldwide. Submission was due on June 15, 1998, right? I think yesterday I sent you one link, if you remember. Something is broken, right? Right, from the NIST submission for the post-quantum cryptography. So you can see that people are trying. So, so what happens normally, NIST issues a call for proposal, people submit, okay, I have designed this crypto system, you please check, and there are committees, discussions. Finally, out of say maybe 100 submissions, they pick up 20, 25 candidates, which can go into the standards, and then again people try to break. Okay, and then maybe 4 or 5 they will select, and then they say that, okay, we know again we need to pick up out of those 4, 5, 1 or 2, maybe we should go to the as a standard thing. So this is very, I mean, now a systematic process basically. So submission was due on June 15, 1998. So in August, out of 21 submissions, 15 met all the criteria that was proposed. So basically, what kind of criteria was there? As I mentioned about the security and the cost effectiveness, easy algorithm, implementation should be easy, and so on. So first AES candidate conference happened actually in August, and second happened in March 1999. Second AES conference, the conference people will come and discuss about all these things. As I mentioned, five candidates were chosen by NIST in August 1999 conference. Mars, Mars is a system designed by IBM. RC6. Okay, so this was again from USA. So this third one was from that AES, Advanced Encryption Standard. Rajendra designed this from USA. This Serpent was from Europe, and Two Fish was again from USA. Okay, so these five candidates, one, two, three, five candidates were chosen, and then the third one became the standard, the AES standard that was adopted finally. So in April 2000, third AES conference, where this was finally decided, so was selected actually in October finally, was selected as the AES, which is the actual standard. So NIST then in February 2001, NIST draft for FIPS for AES was released, and November 26, 2001, it was adopted as standard, and December 4, 2001, published in FIPS, publication, the Federal Register. So basically, I think this is available. You can go to NIS website, NIST website, and you can download this standard. I have also downloaded. I can put it in the lecture folder if you want. So that's the standard. You can look at it. So this was a little bit history about AES. Now, what is the structure here? So I'm going to describe 128, AES 128. So basically, input bits are 128, and key sizes I'm taking 128. Normally, what happens? So there are a bunch of rounds in the so 128-bit plain text is coming as input. Then there is there are a couple of rounds. So pre-round transformation. So normally it is addition with the round key, and then there are different round 1, round 2, again the keys are added, and so on. Finally, certain number of rounds, and there is slight difference here depending upon which one you are using, and output is 128-bit, right? And here there is an algorithm from some master key. You are generating all these round keys, K0, K1, K2, K3, and so on. NR is a number, so now what happens for AES 128, when the key size is 128, number of rounds are 10, and I'm going to describe this where the number of rounds are 10. For 192, there are 12 rounds, and 256, there are 14 rounds. Okay, so this is the general specification. So so how many rounds you will choose depend upon which AES you are choosing. So AES 128, 192, and 256, right? So we are going to focus on AES 128. So I'm assuming here now that we have 10 rounds basically. Okay, round 1, round 2, round 3, and round 10. Okay, and then there is a pre-round. Okay, the last one is a little bit different, so which I'll tell you what happens in each round. Any question at this point? So first and last round are little different. Okay, I'm going to tell you more about. So first round is something, last round is something, and in between all other rounds are similar. Okay, so we do something else in the first round and the last round. In between all rounds, they use the same mechanism. Okay, this is the general process. And obviously, so basically there are a bunch of, so plain text as an input, ciphertext as the output, size is 128 bits, and there is a key generation mechanism which will generate keys, round keys, which you use in the system. Okay, this is the general thing. Okay, so now how high level description, what happens? So first thing is key expansion. From that master key, you generate keys, that round keys, K0, K1, K2, K3, right? So there has to be some mechanism for that, some algorithm, which is fine, using this key schedule. Then we have initial round, or we also call it pre-round. In this initial round, we just add one round key. each byte of the state is combined with the round key using bitwise exclusive OR. Okay. Okay. So this is pre-round, just adding round key, nothing else. Okay. In the pre-round, then rest of the round 1, round 2, round 3 up to round 9, we do these 4 operations. I'm going to explain what are these 4 operations: sub bytes, shift row, mix column, and add round key. Okay. So sub bytes, shift rows, mix column, add round key, and last final round we have sub bytes, shift row, and round key. Mix column is not there. Mix column is not there. So in all the other rounds, these 4 things are there. So actually mix column is not there, but rest of the 3 are there in the final round. This is the high level description. Any question at this point? I hope it is clear. 128 bits are coming. 128 bits are final output. Okay. In between there are rounds. First round and last round is a little bit different because first round we are just using add, that round key, add round key. And the last round we are doing sub byte, shift row, and add round key, and no mix column. Now, in all other in intermediate rounds, we have these 4 operations: sub byte, shift row, mix column, and add round key. So I'm going to explain each of these things in details, how it works, right? Fine. So this is the general strategy. Now you see, yeah. So we are zooming a little bit more overall structure. So the second column, if you see, plain text 128 bits are going into the system. Now key, the schedule key, the round keys. How do we generate the round key? By some algorithm which I am not telling you right now. But from the master key we generate certain round keys, and these round keys, so like W0, W1, W2, W3, and so on, W4, W5, W6, W7, and so on, W40 up to W43. So there are total 44 such keys here. So basically, the first round, the pre-round, we only add key. So which is W0, W1, W2, W3, which you add. Okay, we call them cipher keys. Okay, so there is a general master cipher key, and then there are sub keys. Okay, so first pre-round, we are just adding round key, right? Then the next cipher key, so W0, W1, W2, W3 is added to the first, in the first round, the pre-round. And then the first round, we have this thing: sub byte operation, shift row operation, mix column, and then you add next keys in the schedule: W4, W5, W6, W7. Okay, into this round 1. Then go to the next round and do the next one, and so on. Finally, we have W36, 37, 38, 39 in round 9. Okay, and then finally round 10, mix column is not there, right? As I mentioned, round 10, and then we are adding this. So basically, how many such things are there? 44 such keys are there, right? Okay, because from round 1 to round 10, there are how many keys? 40, right? And then the first one is using 4, so 44 such keys are there, right? So key thing to observe, there is no mix column, okay, here. And then, of course, then this is the reverse part, which is okay. So reverse, add round key, inverse shift row, inverse sub byte, no mix, inverse mix column, and keep on doing. Finally, we get the plain text. So this is a very, very, again, high level description. So I need to tell you, how do we generate? So first of all, I'm going to focus on this each round, okay? Sub bytes operation, shift row operation, mix column, and add round key, right? But first of all, I need to understand the data structure. So we have 128 bits. So actually, these 128 bits we need to arrange in the form of 4 by 4. So 128 bits, what? So 16 into 8, right? So we can divide into blocks of 8 bits. 128 bits, I can divide in blocks of 8 bits. 8 bit, 8 bit, 8 bit, 8 bit. 8 bit is equal to 1 byte, right? So basically, we are having 4 cross 4 matrix. The data format is 4 cross 4 matrix. Okay. So because there are 16 values will be there, right? Each value will be 8 bit, means 1 byte, right? Like that. Now also, each byte, because each byte has 8 bits, so basically I can divide half, 4 bit, 4 bit. Each 4 bit we use hexadecimal notation. Okay, so actual data entry is in the form of hexadecimal notation in 4 by 4 matrix. Okay, that is how we think about the structure. I'll show you the picture also. Okay, so this is how, and the same thing for the key, right? So let me show you. So 128-bit value. So data block viewed as 4 by 4 table of bytes. You see something like this. 4 into 4, 16, right? So 8 bits here means 1 byte, 1 byte, 1 byte, 1 byte, right? Now, right? So this is the whole thing, right? And you know, so these actually, when we look at key is expanded into an array of 32 bits word. Okay, so each one, so W0, this is one word, second, third, fourth. So these you can look as a column. So each one, W0, W1, which I told you there, is this kind of column. W0, W1, W2, W3. Okay, these are columns. These are known as words. Okay, keywords. Okay, keywords that you use. Okay, so there are two things you need to remember. First of all, key has to be in this 4 by 4 matrix format, which I have shown you in the form of W0, W1, W2, W3, these kind of columns. And actual plain text, 128-bit, that also you need to arrange in the form of 4 by 4 matrix, right? So that is our data on which key will be operating, right? So we are adding 4 by 4 matrix with a 4 by 4 matrix where each entry is a 2 pair of hexadecimal. Why 2 pair of hexadecimal? Because everything is 8 bit. 1 byte is equal to 8 bits, 8 bits is equal to 4 bits, 4 bits. Each 4 bit corresponds to one hexadecimal value, right? So 2 hexadecimal value in each block, I mean in each entry, right? That is the key thing. So as I mentioned, so basically, these are the all 16 bit patterns, right? Because 4 bits will give you all these 16 hexadecimal representation. So for example, if you have 8 bit like 0 1 0 0 1 0 0 0, so this will go to 4, this will go to 8, so this will become 48. This is the hexadecimal value at one entry in the matrix. Okay, one each entry in the matrix is hexadecimal value. Any question at this point? Clear? Each entry is a hexadecimal value, right? Okay, so this is so normally row or column we can think as a bird, as a word and so on. Let me show you. Plain text. So suppose we have this plain text, something like that is written, right? So we know that everything gives you ASCII value, 8 bits, right? So each 8 bit will correspond to 4 bit hexadecimal value. 0 0 0 4. These are all hexadecimal values, right? Got it? And then, so this is our plain text which is entering into the system. I'm converting into the hexadecimal stream, and then this hexadecimal stream, you see 0 0 0 4 1 2 1 4. Read this, and then go to the next one, 12 0 4 12 0 0. Like that, you fill the matrix 4 by 4. This is our state. Got it? So basically, our plain text, which is a ASCII string, right? Byte string. That byte string is converted into hexadecimal values, and then you arrange them into 4 by 4 like this. Okay, this is our data on which we are going to operate. Okay, and then we have the key. Okay, key is also 4 by 4. Got it? Any question again at this point? It is clear? Plain text convert into byte strings, basically 8 bit, divide into 4 bit, and pair of hexadecimal values for each 8 bits, right? And then you arrange them in the form of this matrix, 4 by 4. Now, again, now since we are working with 8 bits, so 8 bit means आगे हमारा पुराना, right? That field, finite field with 256 number of elements, right? So because we are doing all operations in that field, so I need to form a rule. So essentially, it's very simple. What you do, you design the rule for arithmetic of over field with 256 number of elements, and then use him as a lookup table, right? For when you write a program, right? Just use those things, So let me show you few things. For example, this field with 256 number of elements, we can generate using a irreducible polynomial which has no root in the ground field of degree 8, x raised power 8 plus x power 4 plus x cube plus x plus 1. Okay, and you can form field with 256. This is very important and basic building block, because for all data operations we use this, because all your data is in the ASCII format, 8-bit size. Each of those 8 bits correspond to an element in this field, right? And do all the operations over this. Okay, it's very important. So, for example, if you have these two elements in the finite field, this will become this. In terms of polynomial representation, we have this. In terms of bits, we have 8-bit plus 8-bit is equal to another 8-bit, right? Which is in terms of bit representation. And if you take 4-bit decomposition, you get hexadecimal values, right? So hexadecimal sum is the next one, right? This is everything in the form of hexadecimal. So you can make a table. Everything is a hexadecimal, make an addition table. You can do that. Similarly, you can do for the multiplication also, right? So same thing for the hexadecimal, same thing. So with the hexadecimal notation, the whole finite field operations for addition table and multiplication table can be defined. Okay. Any question at this point? Okay, clear? Similarly, you can have the multiplications like 57 into 83 is equal to C1 in terms of hexadecimal, right? You again make a table and do all those things. And essentially, you can see the calculations, that polynomial into this polynomial into the other polynomial will give you this polynomial, reduce it to with a reducible polynomial, x is for 8 plus 4 plus xu plus x plus 1. You simplify it to this polynomial, right? And this, again, you convert into 8 bits. And those 8 bits, 4 bits, you get as a hexadecimal value C1, right? Got it? So you can do the multiplication and addition, right? In fact, there are some simplifications as well, which I'll just quickly mention, rather going into details. But these are important for the exam point of view as well. I'm telling you right now, right away. Okay. So basically, multiplication by x. So basically, if your binary polynomial is defined like this, degree 8, right? So multiplication by x, that is by this number, or in hexadecimal value 0, 2 actually, can be implemented at the byte level as a left shift at a subsequent conditional bitwise OR with 1b. This is an observation which is used quite a lot, right? So I'm not going to details, but I'll leave it to you. Slides are there. Enjoy the beauty of finite fields here, right? So in terms of hexadecimal notation. Okay. So any question up to this point? You understood how the data is coming arranged in the form of 4x4 matrix. Each entry of the matrix is a byte, essentially 8 bits, essentially a pair of hexadecimal value, right? Now I am going to look at what happens in each round. Okay, so let me show you what happens in each round. So we have a state which is 4x4, which is coming inside. And remember, in each round, we have sub byte operation, shift row operation, mixed column operation, and round key. These 4 operations we are doing in each round. Okay. And then so output is again a state 4x4 matrix. So 4x4 matrix consisting of pair of hexadecimal values goes as a input, and 4x4 matrix consisting of hexadecimal value comes as an output. In between, I have to do these 4 operations: sub byte operation, shift row operation, mix column operation, and add round key. So these 4 operations. This is from first round till 9th round. These things are there. Pre-round, before first round, we only add round key before the first round, right? And in the last round, this thing, mix column is not there. Remember, as I mentioned again and again, same thing, right? So the last round we don't have third transformation, mixed column is not there. Okay. This is still, it's a very general thing. Now I have to go and you see the beauty, how the sub byte operation works, how the shift rows works, and how the mixed column works. All over finite fields. The beauty of finite fields you can use to design things. Okay. So essentially, as I mentioned, the input bytes are something like this, right? 4 by 4. Each one is a pair of hexadecimal value, each entry here. And then you apply something, you again get 4 by 4 state array at a given point of time, and output is finally this kind of thing. So this is the intermediate state which is happening, right? This will keep on changing. Something is going, operation, another go to the next level, another operation, and finally we have the output. Okay, 4 by 4. Just remember this fact. So now the first operation, sub byte operation. Sub byte operation is a beautiful thing you observe. So what happens? You look at 4 by 4 matrix, look at one particular entry, which is a pair of hexadecimal value. Okay. So use one S. So now we are using S box of 16 into 16 bytes containing a permutation of all 256 8-bit values. I'm going to show you the how it works. So then each byte of the state, each byte, that means that pair of hexadecimal value in the 4 by 4 matrix is replaced by a byte indexed by row, left 4 bits, and column 4 bits. So you read the byte, there are 8 bits, which is pair of hexadecimal value. So look at the, the first 4 bit will give you row number, and second 4 bit will give you the column number, row and column. Then you look at this S box, and in the S box table, read that row and that column and see whatever entry is there. So replace that entry in the previous 4 by 4 matrix to the next 4 by 4 matrix. That entry will be replaced. Okay. So let me show you. For example, 95 is replaced by byte in row 9 in column 5, which has value 2a. So let me show you. I will show you how this S box is constructed, but first how to use it. Let me show you. You see? So we look at, suppose this entry is 9 5, pair of hexadecimal value 9 5. Okay, so 9 is first 4 bit, 5 is last 4 bit. So this is telling us that you look at in this S box matrix, okay, which is a 16 by 16, look at 9th row and 5th column, this entry. So take this entry and replace with this value here, you get here replaced. So output is something like this. Okay. Everything this you have to do for each bit. So each 4 by 4. So in each 4 by 4 state, right? Each 4 by 4 matrix. Look at the entry. Look at the first 4 bit, last 4 bit. First 4 bit, last 4 bit gives you the row number and column number in this S box. Okay. Just read that and replace with that entry, right? And then so this you have to do for each of them, right? So get one this 4 by 4 matrix will be converted into this. So this is sub byte operation. Got the idea? This whole thing is known as sub byte operation, where we are using a S box. So in the last class yesterday you saw S box was those 4 by 16 matrix, right? Here it's a little bit different, but I will tell you how to construct that S box also. But given that this kind of S box matrix is there, right? So I just use this, right? 4 by 4, and you do this replacement. Any question at this point? Sub byte operation. Okay, so basically, now S box constructed using defined transformation of values in Galois field. So this S box is constructed with this machinery of Galois field with 2 raised power 8 elements, 256. Here is the substitution. So basically, this is our polynomial. So sub byte operation is D is equal to X times SRC inverse, that's matrix value inverse, plus Y. Y is a fixed vector. This is the operation to get you this sub S box matrix. And there is similarly inverse, which I am not doing the calculation, but probably you can see that inverse works actually exactly in this. When you do these operations over field with 256 number of elements. Okay, so these two operations, sub bytes and inverse sub bytes operations, are inverses of each other. Okay, so this is the formula that we are going to use to construct. So let me show you. So basically, if you look at again, you see multiplicative inverse of 0C in G of 2 raised to 8 is B0. Okay. So let us show you how 0C transform into FE by a sub-byte routine. So basically, what we are doing is here, this thing, you see. I'm going to use, there is a matrix representation of this thing, which I'll show you how it is used. So I'm going to show you for this one, D is equal to X times SRC inverse plus Y. Okay, how this is basically implemented in the form of matrix here. So this is the matrix actually. How do we build it? So let me show you. So 0C, so multiplied inverse of 0C in this field is B0. B0 is, like 10110000. The hexadecimal value is 4-bit, 4-bit. So that means this vector B is this thing. So multiplying matrix X by this matrix results in C. Here is a matrix. So this is the vector B will come here. And this is a matrix actually, fixed matrix. X is a fixed matrix. You multiply this and you get C value. Okay. So here is a C. So this is the C value. You will get 1001 and 1101, right? So you 0C inverse is B0, which means B is this. Take that as a column, multiply with a fixed matrix X, and you get C vector, C value, which is this here, 10011101, right? So, and the matrix is given here actually. Here is the matrix given here. So you multiply with C, multiply with this, you get C values, right? And then you add here, this vector is Y here to get D as the output. Okay. So D here is the result of XOR operation is D when Y is that fixed vector. Okay. So you get D is equal to 1111 and then 1110, which is hexadecimal notation FE. Right. So this is how the whole operation is implemented. So D time problem. Look at those operations which I given you, in terms of the form of a matrix actually. Just verify that what we are doing. So I'm giving you that. Note that whatever I have. So this operation correspond to this kind of matrix form. So basically, just verify this. I'll leave it to you to just verify this. Okay. Similarly, we have the inverse byte operation, which is result operation. This is the inverse byte operation. Okay. So this is how it works. Okay. Here is a sub-byte table actually. So everything, of course, once you make a table, S box is fixed, and you just use the operation, sub-byte operation, right? So the beauty is, how do we construct the sub box from that finite field machinery? So it requires 1 or 2 cup of tea for you to enjoy, right? Because now I hope you have the the background to actually do these calculations. Okay. So for example, you see that here, that 9th row, 5th column is 2A. That's why that thing is replaced with 9-5 is replaced with 2A. This matrix is used. So essentially, as a programmer, you don't care how we are getting this S box. You just encode this matrix in the program and you do the job, right? Which is fine, but you should also understand how to get this matrix, right? Okay. Maybe tomorrow you can present a new crypto system, so you should know how they are thinking about these things, right? Okay. This is inverse sub-byte table. You can also compute the inverse sub-byte table, right? So as I mentioned, so this is the state value, for example, sub-byte operation. You can check any of them. Say 1-3 will go to 7D, 1-2 will go to C9 using sub-byte, and the inverse sub-byte also you can verify. Right, the table is there, right? You just read row number, column number, is move it, right? Okay, so I hope you got it, right? Sub-byte operation, inverse sub-byte operation. अभी तो मैंने केवल एक ही चीज देखा है उसमें से, sub-byte operation. Sub-byte operation using through some S-box matrix, okay? And there is a mechanism to construct that S-box matrix. Now shift rows. Shifting which permutes the bytes. A circular byte shift in each first row is unchanged. So if this is a matrix, first row is unchanged. Second row does 1 byte circular shift to left. You can see that we have shifted here. And the third row does two byte circular shift to left, and fourth row is 3 byte circular shift to right. Right. So all shifted. Okay. This is the shift operation. And in the decryption, the transformation called inverse shift rows, and the shifting to the right rather than to the left. Okay. So this is the shift row. The first operation was sub byte. Again, I am just recalling. So I talked about sub byte operation, which involves S box, right? Shift row, I've told you. Now I am going to tell you mixed column operation. Okay. What is mixed column operation? So this is shift row, shift column. I mean, right? The inverse shift row, mixed column. So shift rows and mixed column provide diffusion to the cipher. Each column is processed separately. So what we do here, we have a matrix. Look at a particular column in that matrix, multiply with a constant matrix. This matrix is fixed, and you get something in the column. Read a column, multiply with this matrix, and get another new column for the matrix. That's what we are doing. Okay. So here is mixed column scheme. So we have this 4 by 4 matrix. Look at the first column, and this matrix is fixed: 2 3 1 1 1 2 3 1 1 1 2 3 3 1 1 2. So that first column goes in here, multiply, you get the resultant column, which is put here. Okay. Then read the second column, do the same thing, replace with the second column the new one. I mean, third column, right? I mean, so you just keep on doing, right? Read the first column, do this operation. Second column, third column, fourth column. There are only 4 columns. So this is mixed column. Okay. Very good. So here is a, you can verify this 4 by 4 matrix. This column is 0 2 0 1 0 1 0 3. Then you multiply with this matrix, get the new column as this. This is what you need to do. Okay. So whatever you can do in forward, you can do the reverse direction. Inverse is also there, right? So you can do the inverse also, which is okay. Now, round key. How we should add round key? This is a little bit, I mean, involved, but not too much. But let me see. How do we go this round key? So we have our data is a 4 by 4 matrix. Each value is pair of hexadecimal value. This is our data point, right? And we have done all these operations on those data points. Now I need to look at the adding round key. Round key is 128 bits. The master key is 128 bits. From that we will get through some scheduled round keys, right? K0, K1, K2, K3. For each round we'll have one round key, right? Now I have to add that round key. So now I need to find a 4 by 4 representation of each round key also, right? So now what we can do is 128 bits. I can convert it into them 4 by 4 matrix, right? Because what happens? 128 bits, 16 into 8. Again, we can actually convert, right? So then you just add one state with the round key and just bit by bit addition. So each entry in one matrix added to the other matrix, right? Bitwise operation. So here is something I should say. So this is our data point, those plain text which is coming as a matrix. Now, in each round, you remember if you look at, I'll show you the picture. So I'm saying that each word, W0, W1, W2, W3 is added in the first case. Second case, round key was, W4, W5, W6, W7, like that. 44 keys were used, right? So each key we are taking as a vector here, and you just operate into the each vector here in the column vector and add, and you get something like this. Okay. So those W0, W1, W2, W3, we are acting as a vector. Okay. So finally, we have this round. We have a state. So I think maybe I should show you. what I'm talking about here. You see, this is the structure. So what I'm saying that those vectors are added here, W0, W1, W2, W3 to that box every time, right? Here, 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 in all, right? Round keys are added. Okay. So now the overall process, how does it looks? Here is the whole thing. Different rounds. State is there, sub byte operation using S boxes, another state, shift row state, mix column state, add round key, and state, there is a final state. So this is starting from one state to this is the whole procedure, what is going on in the whole AES business, right? So now, last thing about the key, right? So basically, from the master key, that master key 128 bits, when we generate those key schedules, right? So it takes 128 bits, means 16 byte key, and expands into an array of 44. In the our scheme, there are 44 keys you saw. In other schemes, 52 and 62 keys are generated, right? For the other rounds, right? So in our round, it's 44 keys are generated. We start by copying key into the first 4 words, okay? Then loop creating a word that depends on the values in the previous and 4 place back. In 3 or 4 cases, just XOR these together. First word in 4 has rotate, S box, XOR round, and constant on previous before XOR 4 back. I mean, all these things is written, but I can show you the picture which will make it easy to understand. So here is the operation. So you take the whole key, we divide into 4 by 4, and then read them each column as a W0, W1, W2, W3, right? And then you do these operations that G I told you, and you get the next one. I mean, this kind of operations you do, you get the next one and the next one. So basically, the first 4 word pair, key word pairs give you next 4, next 4, next 4 till you get the final one. Okay, this is the whole thing. Okay, so in general, I mean, we have, so basically we have all these words, right? Key scheduling. So pre-round, round 1, round 2. I mean, this is more general for our round. For we have only 10 of them, these things, right? 10 rounds are there. Okay. So this is all about AES 128. I think there are now some rationals about it. Yeah. This is the whole picture, how it works. So basically, you see this mechanism, rotation word and subword and these operations which I mentioned are also described in the form of this algorithm actually here. This is the algorithm, rotation word and subword. So I leave as an exercise for you, right? That is better. Now look at this plain text, ciphertext, cipher key. So you see everything is in the form of hexadecimal. This is plain text, cipher key in the form of hexadecimal, and ciphertext in the form of hexadecimal, right? Now let me show you the example how it is working. So this is our data, input state, pre-round, output state, round key. So these round keys are added to the input state to get the second block, right? Then round 1, we are again doing the same, all those calculations. Round 2, round 3, round 4, this is the actual data. So maybe over a cup of tea, you would like to verify some of the operations here, right? Just verify, whether sub byte is working fine. Is there any mistake you can check? Mix column is working fine, right? Data is there in front of you, you can just check. So this is all up to round 6, round 10, okay? These are all states in a single round. Input state, after sub byte operation, after shift rows operation, after mix column operation, after round key operation. So all of them are given here, right? So you enjoyed the beauty of AES 128. So I invite you to break it. Can you break it? How do you approach? Maybe you can think of. So normally, this both linear cryptanalysis and differential cryptanalysis is not good. So Do you have any other way? See how these people think about these complicated things. You can also propose something. I mean, okay, take say a certain number of bit size, do some operation, right? Certain number of rounds, and see if you can propose something. I mean, it's something, and then make sure that it is secure. I mean, that is one important thing, that it is secure anyway. So AES was designed after DES. Most of the known attacks on DES were already tested on AES. So as I mentioned, in the DES, brute force attack was the one which was working. Uh, in our AES is definitely more secure than DES due to the larger key size. Okay. Statistical attacks. Numerous tests have failed to do statistical analysis of the cipher text. And then differential and linear attacks. There are no differential linear attacks on AES as yet. So the field is open for you to try to break it, right? So if you break it, you will be famous. The ICT will be famous, right? And I can say that it was broken by my class student, right? So thank you very much.